Welcome back to NCERT class 10th chapter number 13 magnetic effects of electric current. Children, after learning all the subtopics of this chapter, in today's session we will discuss some problems based upon magnetic effect. Isn't it, children? These questions might be in your NCERT, that is the in-text or exercise part. Those we are going to solve in today's class, children. Here, the first question comes, which of the following property of a proton can change while it moves freely in a magnetic field? This is what question, and they have given 4 options, that is how it varies with mass, speed, velocity and momentum they have asked. Imagine, children, this is a proton, isn't it? It's a positively charged particle. And imagine that this proton is if moving in a magnetic field. This is what? Magnetic field, isn't it? What is this? This is a magnetic field. It will attain some velocity and moves in a circular path. In the magnetic field, how a proton is moving, children? In a circular path. Means along the magnetic field, the proton will start rotating, isn't it? Means it starts moving. Because of this reason, when it is moving along a circular path, means what happens to its velocity? Velocity also increases and momentum also increases, isn't it, children? So the option here is what? Both C and D are also true here. We can write now here, that is velocity and momentum changes, isn't it? So we can say that a property can change while it moves freely in a magnetic field with the what? Velocity and momentum. Because its mass, there is no effect on a mass and a speed. When it is moving in a magnetic field, its velocity and a momentum will changes, means increases. So you have to answer what? The both options C and D, velocity and momentum. The next comes, how do we think the displacement of a rod in the figure 13.7, that is force on a current carrying conductor? In that experiment, figure is there now in that figure. How this rod AB will be affected? Suppose if current in a rod AB is increased. See, imagine, children, this is what? Rod which have a some length. You can take it's a 5 cm aluminum rod. So how current in rod AB is increased? Then stronger horseshoe magnet if we used, what happens? Then length of the rod AB is increased. It means what is the changes to its the displacement? They have asked here. How displacement is affecting with respect to increase in a current? Suppose if we increase if we use instead of a horseshoe magnet, if we use the stronger one in that horseshoe magnet, how the displacement is going to increase? And similarly, if we increase the length of this rod, what is the displacement is the question. So definitely, children, when the current in the rod increases means the displacement also increases, because more current means more displacement it will show, deflection it will show, more force it will generate, isn't it, children? So we can write here displacement increases, isn't it? Then how it affects by the use of a horseshoe magnet? Definitely what? Displacement of the rod also increases, because more power will be there, isn't it? If more force of attraction means more amount of a displacement will be shown by the rod here. So here also what happens? Displacement also increases if we use a stronger horseshoe magnet. And the third comes what? If we increase the length, suppose for 5 cm the rod is displacement the rod has shown some amount of a displacement. If the same rod, its length got increased, So what happens? More displacement it will show, because length is directly proportional to, here we can say, displacement. If the length of the road increases, means force on that also increases. Because of the more amount of a force, more displacement can be achieved here. So in the third case, length of the road AB if we increased, means the displacement also increases. The displacement also here increases. Isn't it, children? This is what a few questions. We will solve few more. Children, the next question is, the magnetic field in a given region is uniform. Draw a diagram to represent it. Say here, what is the meaning of a uniform, children? Same. Means the magnetic field lines are moving in the same direction. So for such a magnetic field, they asked us to draw a diagram. Isn't it, children? So imagine this is what? One magnetic field which is moving in this direction. Isn't it? So here, if we take more than one, if they all are in uniform, means each and every one magnet is moving in the same direction, uniform, then the diagram would represent, or it would look like this, children, because this arrow is all are moving in a same direction. So now we can say it as a uniform. Isn't it, children? So this is a what? A magnetic field which is uniform. Means all magnetic field lines are moving in the same direction. That is the meaning of a uniform here. They are all moving in a same direction. Isn't it, children? The next, the magnetic field inside a long straight solenoid carrying current is. They asked us, what is the magnetic field inside a solenoid? We already studied that. That is outside the bar magnet. How, children? That is the direction of a magnetic field takes place from a north to south. Isn't it? Imagine that this is a bar magnet. Isn't it? You can imagine it as a now solenoid. Isn't it? Outer side, the magnetic field lines, they are all moving and merging at a, means they will emerge at north pole and ends at a south pole. This is what? From outside. But when you look into the magnet, that is inside the magnet, the direction of the magnetic field is uniform, children. Isn't it, children? Suppose if we check here, the direction would be same. And similarly, if we check at this point, the direction of the magnetic field is same. At this point, means at different points inside the solenoid, the magnetic field is uniform, children. So we can write that magnetic field inside the solenoid is uniform. Means all the magnetic field lines are moving in the same direction. At any point, if we cross check, means it is giving same direction. Okay. Now we will go with the next question. A positively charged particles projects towards west, is deflected towards north by a magnetic field. The direction of the magnetic field is which we need to find out, children. So would look now, imagine this is what? North direction, and this is south, and this is west, and this is east. Here the direction of the current they have given, that is alpha particle movement they have given towards west. So we can write here now, that is what? Direction of current is nothing but a alpha particle which is moving towards what, children? West direction. So in this direction the current is moving, and the deflection is towards north. So what is the direction of deflection, children? Direction of deflection is towards the north. Means towards the north, this is what? Force. isn't it? The direction of a deflection, nothing but a deflection means here motion or force you have to consider, isn't it, children? So the force is towards north and the current is towards the what? West direction, and find the direction of the magnetic field. So children, at this situation or for such a problems, you have to use which rule, children? Fleming's left hand rule. So when we stretch the three fingers of our left hand in such a way that the thumb should be perpendicular to or right angles to index and also to the direction of a current in such a way that this, suppose west, towards the west is the direction of a current. Imagine, children, this is what? The direction of a current now, isn't it, children? In this direction the current is moving and this thumb is giving the direction of a force which is into the board now. Then what is this finger, children? This index finger is nothing but a direction of a magnetic field. This finger is giving what? Pointing towards up. So the direction of the magnetic field is upwards. So you can write answer, children, upwards. The direction of the magnetic field is what? Upwards. Using Fleming's left hand rule we can find out, children. Children, now the question comes. An electric oven of 2 kilowatt power rating is operated in a domestic electric circuit that has a current rating of 5 amperes. What result would you expect and explain? Children, this electric oven, when we look at this question, generally we know that high power rating devices need that is which fuse, children? 15 amperes fuse they need, but here they are connected to 5 amperes fuse. So let us see what happens now, step by step. What are the given things, children? That is power P is equals to 2 kilowatts. Since it is in a kilowatts, children, convert it into watts, nothing but a 2000 watts. So what is the P value, children? 2000 watts is the power value. Then voltage is how much? Voltage V is equals to 220 volts. Then what is the current, children? 5 amperes current they have connected. So first we need to calculate how much current it has used here. So using formula P is equals to V into I. This formula we have to use, children. Using formula. So here, since we want to calculate what? I. So in terms of a I, how can we write this formula, children? P divided by V. Isn't it, children? So I is equals to, what is the P value? 2000 watts. Then what is the V value? 220 volts. Isn't it, children? So this zero get cancels, isn't it? Then 1s or 11s still smaller, you can go. Then 9s 198.091, which is what, children? 9.091, which is equals to 9 amperes we can write. Since it is not exceeding 5 to more, so we can directly write it as a 9.0 or 9 amperes current. Therefore, I is equals to how much? 9 amperes current it has used. So we can say that, suppose if this electric oven, if we connect it to 5 amperes fuse, means the maximum, that is safer limit, will exceed, children. So what happens? The circuit will become now open. Then this 5 amperes fuse starts melting because it consumes a more amount of a current, isn't it, children? It needs what? 9 amperes of a current. So safer limit is exceeding now, isn't it? It uses more than the safe limit. So the fuse wire starts melting and the circuit becomes now open. This is what the explanation, isn't it? Since electric oven needs 15 amperes fuse. Suppose if we use 5 amperes fuse means the circuit becomes open, or the fuse element, first you can write the fuse element melts and the circuit will becomes open. Circuit becomes open. So this is what situation. So generally higher electrical power rating devices should be connected to 15 amperes of a fuse. So what the mistake they did? They have used here 5 amperes. So instead of this 5 amperes fuse, they need to use a 15 amperes of a fuse. Then this electric oven will run smoothly.